Welcome to this explainer. All right, let's just jump right in because this is one of my absolute favorite topics. I want you to start by just imagining yourself stepping outside on a crisp, perfectly clear winter night. You look up into the pitch black sky and you see thousands of twinkling lights scattered across the darkness, right? It's a beautiful, completely humbling sight. But here's the truly staggering part. Every single star you can see with your naked eye belongs to an unimaginably vast island of gas, dust, and dark matter. An island so breathtakingly massive that it contains hundreds of billions of stars of its own. We call these monumental cosmic islands galaxies. And they're literally the fundamental building blocks of the large-scale structure of our entire observable universe. But the universe wasn't always filled with them. They weren't just always there. So how exactly did we get here? How did the universe go from this completely formless, empty expanse to the magnificent, glowing cosmic web of superstructures we see today?
It's a phenomenal question, isn't it? We know from our physical cosmology models that right after the Big Bang, the universe was basically a hot, incredibly dense, and almost perfectly uniform soup of particles. It was strictly homogeneous. Everywhere you looked, exactly the same. But today the universe is incredibly heterogeneous. It's complex, it's lumpy, it's chaotic, and it's filled with planets, stars, and these absolutely colossal galactic structures. Now, if we understand how the very first solitary stars ignited from pockets of cooling gas, the next big mystery naturally becomes, if individual stars existed, how in the world did entire galaxies appear? How did these lonely points of light organize themselves into the spectacular, swirling, gravitationally bound metropolitan cities of the cosmos? Well, to answer that, we have to travel all the way back to the very beginning of the cosmic timeline.
Section 1. The universe's first sparks. From the Big Bang to the cosmic dawn.
Okay, so looking at this early cosmic timeline, the sheer, incomprehensible scale of time we're dealing with here is just absolutely staggering. We kick things off at the Big Bang, roughly 13.8 billion years ago. Now, for the first 380,000 years, the universe was so unimaginably hot and dense that light couldn't even travel freely. It was literally trapped in this opaque plasma. As the universe expanded, it finally cooled enough for the first atoms to form, releasing this blinding flash of light that eventually just faded into pitch black. This plunged the universe into what we call the cosmic dark ages. For millions of years, there was absolutely zero visible light. Just a thickening, cooling, suffocatingly dark fog of primordial hydrogen and helium gas stretching across the infinite void. But hiding out there in that seemingly uniform fog were tiny, microscopic quantum fluctuations. Basically, infinitesimal differences in density that existed right after the Big Bang. Over roughly 100 million years, gravity relentlessly took hold of these tiny imperfections, pulling the gas into denser and denser pockets. The pressure and heat built up until, finally, boom, nuclear fusion ignited. The very first massive stars were born, violently ending the dark ages and bringing the first light to the universe. But, one star does not make a galaxy. It took a few hundred million more years for these earliest stars to begin grouping together into the first chaotic proto-galaxies. And to really grasp how they group together so efficiently, we have to talk about an invisible force that literally changed everything.
Section 2. Dark Matter's Invisible Scaffolding. The invisible architect of the cosmos. So the crucial point to understand here is that when we look at galaxies today, they are spinning so incredibly fast that the gravity from their visible ordinary matter, the stars, the gas, the dust, it simply isn't enough to hold them together. But all the laws of physics, they should completely fly apart. There's no way they should hold their shape. This is where dark matter comes in. Our current and most successful understanding of this cosmic evolution is called the lambda CDM model. Think of it this way. Right after the Big Bang, ordinary matter, that hydrogen and helium gas, was just way too hot and energetic. It was bouncing around with too much radiant energy to settle down and clump together. But dark matter? Dark matter is different. It doesn't interact with light or radiation at all, making it completely invisible to us. But it has mass, and therefore it has gravity. Because it was cold and sluggish, dark matter began clumping together much faster and much earlier than ordinary matter. I want you to imagine dark matter as the invisible, deep valleys in a vast cosmic landscape, and ordinary matter as the rain. The rain naturally flows down and collects in the deepest valleys. Or here's another analogy for you. Think of dark matter as the invisible roads, foundations, and scaffolding around which the glowing cosmic city of a galaxy is ultimately built. Without this quiet, invisible architect doing all the heavy lifting early on, the spectacular galaxies we see simply could not have formed.
Section 3. The birth of disks. Spinning up the first galaxies.
This incredible journey from primordial gas to a beautifully structured galaxy perfectly illustrates the bottom-up theory of galaxy formation, which is for sure the most widely accepted model today. Instead of one giant, massive cloud collapsing into a full-sized galaxy all at once, the universe started small. First, ordinary baryonic matter, that cooling hydrogen and helium gas, finally fell into those invisible dark matter halos we just talked about, forming small, dense clumps, roughly the mass of globular clusters. Then, gravity did what gravity does best. It relentlessly pulled these small clumps together. They merged, accumulating more and more mass. And as they merged, they exerted these massive tidal torques on each other, giving the entire massive system a spin. Because angular momentum has to be conserved in physics, as this colossal cloud of cooling gas contracted toward the center, it began to spin faster and faster. Think of a spinning ball of pizza dough. As the chef tosses and spins it, it flattens out, right? The baryonic gas did the exact same thing, flattening into a tight, incredibly dense disk. And inside these dense, flattened disks, the gas became gravitationally unstable, breaking apart into smaller, chaotic clouds that furiously ignited into billions of stars. That is exactly how the very first spinning, disk-like spiral galaxies were born out of the darkness.
Section 4. Violent collisions and mergers. Galaxies as living, evolving ecosystems.
Now, a galaxy isn't just a static collection of stars. It's actually a dynamic, terrifyingly powerful living ecosystem. At the heart of almost every single giant galaxy, and yes, that includes our own, lies a supermassive black hole. And when I say supermassive, I literally mean ranging in mass from millions to billions of times the mass of our sun. That massive scale is incredibly important because there is a direct mathematical scaling relationship between the mass of that central black hole and the mass of the galaxy's host bulge. They grow together in tandem. But this growth isn't just about the black hole gobbling up gas. It's a continuous, living cycle of stellar birth and death. Massive stars burn through their nuclear fuel quickly and detonate in spectacular supernova explosions, and that recycles heavy elements back into the gas clouds to forge the very next generation of stars and planets. But listen, this internal, cyclical growth is really only half the story of a galaxy's life. The other half, that comes from the outside through some of the most violent, monumental events in the entire universe.
Galaxies are living systems that constantly change, warp, and evolve over billions of years. They grow continuously by accreting more cold gas from their vast surroundings, funneling it inward to fuel continuous star formation and feed that monstrous central black hole. But remember that bottom-up model we talked about? Well, the merging didn't stop in the early universe. Galaxies are constantly drawn toward one another by the immense overarching gravitational pull of those dark matter halos. And when galaxies collide, it is an absolutely epic cosmic event. But actually, these aren't quick car crashes. They're agonizingly slow-motion cosmic dances that take hundreds of millions of years to unfold. While individual stars rarely hit each other, mostly because the space between them is so unimaginably vast, the massive, sprawling clouds of interstellar gas violently smash together. This immense frictional interaction creates monumental gravitational shock waves that ripple through the gas, compressing it and triggering a ferocious firestorm of new star formation that we call a starburst. Minor mergers, like a large galaxy slowly absorbing a smaller dwarf galaxy, add mass and subtly shift the outer structures. But major mergers, when two massive spiral galaxies collide head-on, that can completely destroy those beautiful spinning pizza dough disks we talked about, completely scrambling the stellar orbits and changing the galaxy forever.
Section 5. The quenching of galaxies, blue clouds, and red sequences.
So let's see how all of this crazy evolution builds into the fundamental duality of the cosmos that astronomers actually observe today. When we plot galaxies on a color magnitude diagram, they overwhelmingly fall into two very distinct camps. On one side, we have the blue cloud. These are the youthful, vibrant spiral galaxies. They're thin, dense, fast-rotating, and absolutely packed with cold gas and dust, making them active, churning factories for hot, new blue stars. On the other side, we have the red sequence. These are elliptical galaxies. Remember those violent major mergers I just mentioned? Well, when two spirals collide, the resulting gravitational chaos scrambles the neat orbits of the stars so they no longer rotate in a flat disk, but instead they just swarm randomly, kind of like bees around a hive. These elliptical galaxies are massive, shaped like giant footballs or spheres, and populated almost entirely by old, cool, red stars. They are essentially dead galaxies. Of course, the universe is a messy place, so not every galaxy fits neatly into these two camps. We also have irregular galaxies. These are chaotic, completely unstructured clumps of stars and gas. They're often the cosmic wreckage of recent violent collisions or intense gravitational disruptions that simply haven't yet settled into a discernible shape, lacking the beautiful spiral arms of the blue cloud or the smooth glow of the red sequence. But focusing back on the red sequence for a second, how exactly does a galaxy die?
This brings us to one of the most fascinating and, honestly, dramatic mysteries in modern astrophysics: quenching. Quenching is the sudden, catastrophic shutdown of star formation within a galaxy. Because stars form exclusively out of cold gas, a galaxy basically dies when it runs out of that fuel. But the really strange thing astronomers noticed is that quenching happens way faster than a galaxy could simply use up its gas reserves. Something violent is actively shutting them down. Current models point to two main culprits. The first is preventive feedback, which is often called strangulation. As a galaxy gets pulled into a densely packed galaxy cluster, gravitational and fluid interactions strip away its outer layers of gas, literally strangling its supply of fresh material. It just can't accrete new gas to make stars anymore. The second mechanism is ejective feedback, and this one is much more explosive. Remember those central supermassive black holes? When they gorge on too much gas too quickly during a merger, they release unfathomable amounts of energy, shooting out tightly focused, blindingly fast jets of energy and radiation. These jets are so unbelievably powerful, they can physically blow the remaining cold star-forming gas completely out of the galaxy, turning a vibrant blue cloud spiral into a dead, passive red sequence elliptical in a cosmic blink of an eye.
Section 6. The future of our galaxy, the Milky Way, and beyond.
All right, let's bring this all the way home to our very own cosmic neighborhood. The Milky Way is a spectacular, massive, barred spiral galaxy, and it's incredibly ancient. Some of its oldest known stars are estimated to be around 13.6 billion years old, meaning our galactic home began forming very shortly after the Big Bang itself. It contains an awe-inspiring 100 to 400 billion stars. Our little solar system sits on the inner edge of one of the spiral arms, about halfway out from the galactic center. When you really take a step back and think about it, it emphasizes how incredibly fragile and small humanity's place really is. We are just a tiny, microscopic puzzle piece suspended within this magnificent, ancient, rotating disk. However, modern observations suggest that the Milky Way, along with our nearest major neighbor, the Andromeda Galaxy, may currently be undergoing a slow quenching transition. Yep, we're slowly moving from being an active, star-forming blue galaxy to becoming more passive and red. But I'll tell you this, our structural evolution is far from over.
Because in less than 5 billion years, our peaceful rotation will come to a breathtakingly chaotic end. You see, the Milky Way and the Andromeda Galaxy are gravitationally bound to one another, and they are currently hurtling toward each other at incredibly high speeds across the cosmic void. Just imagine the view from our solar system. Over millions of years, that faint, hazy smudge of Andromeda that we currently see in our night sky will grow larger and larger, more menacing and magnificent, eventually completely dominating the heavens. Then, in about 5 billion years, these two massive spiral galaxies will physically collide. It's going to be a spectacular cosmic dance of gravitational forces. The beautiful sweeping spiral arms of both galaxies will be violently torn apart. Massive gas clouds will compress, triggering monumental shock waves and a final brilliant burst of star formation. Eventually, the two supermassive black holes at their respective centers will merge into one, and the chaotic orbits of hundreds of billions of stars will settle into a brand new configuration. The Milky Way and Andromeda will cease to exist as we know them, reborn together as one single, massive, dead elliptical galaxy on the red sequence.
Zooming all the way out now, we realize that our Milky Way's dramatic story is just one among trillions. Today, powerful telescopes like Hubble and the James Webb Space Telescope are piercing through the cosmic darkness, looking back billions of years in time to observe the very first sparks of starlight. They're unraveling the invisible mysteries of dark matter halos, tracking the epic mergers of galaxies across eons, and mapping the large-scale structure of the cosmos. And what they've revealed is an interconnected, glowing cosmic web. It literally looks almost exactly like the neural pathways of a brain on the grandest possible scale. Just glowing clusters and filaments made up of billions of evolving galaxies separated by unimaginably vast, pitch-black voids. We are quite literally witnessing the universe building itself, transforming from a simple, uniform cloud of hot gas into a staggering tapestry of superstructures, a process governed entirely by gravity, dark matter, and the relentless marching scale of cosmic time. I really want to leave you with this final thought. When you step outside and look up at the night sky again, remember, every star you see tonight belongs to a galaxy. Every galaxy is a city of stars. And among the billions scattered across the universe, one small spiral galaxy became the home of everything we have ever known. We are literally made of the gas and dust recycled by generations of long-dead stars within this spinning disk. We are the universe, looking back at itself, trying to understand its own majestic creation. So as we continue to map this incredible cosmic timeline and discover what lies beyond our galactic shores, I have to ask you, what other breathtaking secrets do you think are waiting to be found out there in the deep, dark spaces between the stars?